Hello everyone, I am your beloved TA Samuel. Unfortunately today Matt cannot join us on this video, but it's fine because let me introduce you to our other beloved TA, Nathan.
Hello everyone, I'm Nathan.
Hi Nathan, nice to meet you Nathan.
Nice to meet you too, although this
I'm
isn't the
Sam.
first time. So today, what are we going to be talking about, Sam?
Well, as you can see, we have some transmission line stuff here. We have a beautiful Smith chart on the side. We're actually going to talk about stub matching today.
Stub matching.
The idea behind stub matching.
Wow, sounds hard.
Sounds hard. I think so too. I used to think so. This is the circuit we're looking at today, where we have some arbitrary load impedance and some line impedance. And we have said that both of them are not equal. So Z load is not equal to Z naught. What's an observation we can perhaps make out of this?
So right off the bat, I guess you can say, because the impedances are mismatched, if a voltage wave comes in, like so, then when the wave hits the load, then there must be a reflection.
Makes sense to me. Maybe let's see how it turns out on the Smith chart. Let's pick some arbitrary Z load. Let's call it here Z load. And then let's draw a beautiful circle around it.
Let's.
So in tests, students would use a compass and draw a better circle than this one, because anything less than that would result in deductions in mark.
That's quite the circle you have there.
Despite our leniency, we don't tolerate non-circular circles on tests. So we pick some arbitrary Z load point that is not in the middle. So it's not fully to reflect that they're not equal. When you look at the wave impedance at various points on this transmission line, say you start from the load and you look at points closer to the generator, you would be looking at points around this circle that we've drawn on the Smith chart. Would you agree with that?
I would agree.
And we can say that at any point, the gamma can be read off from the distance to the center.
But wait a minute, Sam. Doesn't that mean no matter how many times you rotate, gamma won't be zero and thus you'll have a reflection?
That is right. So however long you make the line, wherever you look at on the line, there is a reflection whenever Z load is not equal to Z naught. What can we do?
I mean, in circuits, we've added things in parallel to kind of offset balances, or offset imbalances, I should say. Why don't we try that here?
Well, let's try that. So what do you propose we add?
Well, the simplest thing we can add, I suppose, would be just a length of wire.
Just some random wiring that does not attach to any load or anything?
The easiest thing would just be to take some of our existing transmission line.
So just a line that is short circuit at the end.
Exactly.
Wow, that sounds like black magic to me. Perhaps where should we add this on the transmission line? Can we just add it at any point we want?
Well, I would say that because what we want to do is make gamma equals 0,
Yes.
then this is equivalent to saying we want to make the input impedance is equal to 1. Would you agree?
Okay, so 1 plus no imaginary
Plus
component, right?
J0, that's correct.
Okay.
And that would result in, if we're adding something in parallel, I guess we should work with admittances instead.
Oh yeah, so you can just add them. You don't need to take the inverse and all that good stuff.
So that means that the input admittance should be also 1 plus J0.
Yes, because 1 over 1 is just 1. Simple math.
So right now we have an input admittance that isn't 1 plus J0. But I guess the first step we can take is to make it 1 plus j something.
Okay. Well, we have the Z load here, so let's start with converting it to admittance. The load admittance, Y load. And then we want to find a point on the line where the real part is 1, right?
Exactly.
So we just rotate towards the generator because we start from here. So also the Y load. We start from here and we want to find a point on the transmission line where the real part is 1. So we rotate clockwise towards the generator and get around here where it's intersecting with the R equals 1, real number is 1 circle.
The unitary circle.
Unitary circle, yes. And then we keep going, we find the other intersection. And there are 2 intersections, 2 possible locations to insert our stub on the transmission line, right?
To result in this.
In fact, if we just keep rotating, we would hit the 3rd point and 4th point, and we can, if the transmission line is long enough, then you would have many possible insertion locations. Is that correct?
That's correct.
Okay, but we don't need to worry about that. Let's just worry about the first 2 possible points. Okay, so if we look at this point, we see that the real part is 1, and the imaginary part, if we trace the imaginary circle, it's around here. It's plus j 0.7, roughly like that.
So right now,
so at this location, maybe
at that location,
mark it with another color. At this location.
So let's say that would be the input admittance at Z is equal to 1 plus j 0.7.
Okay, okay. And we want to make
it's a little bit blocked by the Smith chart, actually.
Okay,
so
right.
1 plus j 0.7.
So we want to make this into this. We want this to go away. It's evil. So because imaginary numbers are evil and intangible. So maybe we want what do we want this to be? So we just want this to be negative j 0.7 to cancel it out, right?
And then the admittances would add together to be just equal 1.
It's just that simple? Okay, well, let's just write it down. We want, can I have the thing? Thanks. We want Y, the short circuit stub, to be equal to negative j 0.7.
And let's just label that
so
here.
Then
SC.
These just cancel out. That's beautiful. So how do we determine how long the short circuit stub has to be to cancel it out?
I guess we can start with the fact that a short circuit has infinite conductance.
Okay, so instead of looking at the length first, we just look at this very point, right? At this very point, treating the short circuit stub without any length, it's at infinite conductance and 0 susceptance.
0 susceptance.
So on the Smith chart, it's on this side, right? Because we're now working with admittance, so on this side is 0 admittance. 0 admittance happens when it's open circuit. And on this side, it's infinite conductance. So then current just goes wham, and then it's a short circuit. And perhaps if we start from this point, that direction is still the generator direction, right? That direction.
Yeah.
So if we start from this point and rotate there, we could eventually reach some point that is negative j 0.7. So if we get a line, pretty bad drawing, but that starts from the short circuit point to the negative j 0.7 point, then, and we add the admittances together, then we would end up with an input admittance of just 1 plus j 0.
1 plus j 0. And where's that on the Smith chart, actually, Sam?
1 plus j 0, isn't that just the center?
By golly, I think you're right.
Michael. So it's as if we just, at this point, added a short circuit and then moved that point to the center.
Mm-hmm.
Then wherever we look on the transmission line, however you rotate, the center is still the center.
That's amazing.
So it remains 1 plus j0. So once you add this little short circuit stub, the circuit is matched.
Mm-hmm. Because if our input admittance is 1 plus j0, that must mean that our input impedance is 1 plus j0, which must mean that our reflection coefficient is 0.
0. Huh. So originally, before we add the stub, if some power comes in, some would get reflected. And then we just end up with a messy system. Now just by adding, well, not a truly random short circuit stub, but add one at the right location with the right length, suddenly all power is delivered to the load.
Magical.
Black magic. Welcome to Hogwarts, Mr. Potter.